All right, guys, here we go with our day 5 video, the dreaded dependent and mutually exclusive discussion. So we have dependent events. Those are events whose probabilities depend on each other. So if I have two events like today is Monday and tomorrow is Tuesday, well, they depend on each other because I know tomorrow's Tuesday if today's Monday. But if today's not Monday, then that means definitely tomorrow's not Tuesday. So those are two events that depend on each other. Continue to think about what it depends means in real life. So that's going to help us decide whether or not we have dependent or independent events. Common examples are anything with cards. When you draw a card and you do not put it back in the deck, then technically the probability that you draw a second card of a certain suit or color or number depends on what that first one was. The probabilities are different if you do not put the card back in the deck and reshuffle, for example. So here are some formulas. It's the probability of A and B. What we learned in class yesterday was that you can take probability of A and multiply probability of B, and that's what we did in the examples up here at the very flip back one page. We just multiplied probability of A times probability of B. That's for if they're independent. If they are dependent events, the formula changes slightly. This is probability of A times the probability of B given A. Okay, or you could also use the reverse of that. You could switch all the A's and the B's. It's the same thing as doing probability of B times the probability of A given B. That little bar means given, and we will practice more of that like today, tomorrow, the next day, and so on and so forth. So let's look at a couple examples. You choose two cards from a standard deck of cards. If you replace the first card before you pick the second card, then that means that you have the same exact chance of grabbing a heart the second time than you do the first time. So these are independent events. That is going to be important to note because you're replacing the card. So the probability of grabbing a heart the first time is the exact same as the probability of grabbing a heart the second time because you put the card back in the deck. So probability of heart and heart, since they are independent, I'm able to use the exact same formula that we did earlier above in the notes from yesterday. So probability of grabbing a heart, well, 1/4 of the deck is hearts. And means multiply. If I put the card back in and draw another one, the probability is the exact same because there's the exact amount of hearts in there the first time as there were the second time. It's still 1/4. And means multiply. So again, remember when you have this and symbol, it means multiply. And so that's going to lead us to 1/16 is our probability of taking a heart and another heart. So then we've got a different type of question that says you choose two cards from a standard deck of cards. You do not replace the first card. What's the probability of heart and heart without replacing? And so again, probability of heart and heart is the probability of drawing a heart on the first card is 1/4. It's actually the same thing as, maybe I should 13 out of 52, just to show the difference. Same thing as 1/4, but if you do not replace it in the deck, you have one heart out of the deck, which means you only have 51 cards to choose from then, and how many hearts are left if you already pulled one out? 12. And so if I were to reduce this, I put 13/52 just so you could have it in your notes. There's 13 hearts out of 52 total. That does reduce to 1/4. And then if we're going to multiply straight across here, the 4 and the 12 reduce. And so our answer here is 3/51. That's the reduced answer. And so the question is, what's the difference between number 1 and number 2? And so number 1 is 1/16. Number 2 is 3/51. That's because number 1 is independent and number 2 is not independent. That means that they are dependent. My daughter's watching cartoons in the background. So that means that if you draw a heart on the first draw, what are the chances you draw a heart again? That depends on the first one. So the first one's a heart. That means that the chances of drawing a heart again are slightly different. That is exactly what dependent means. And so example number 3, we've got a satchel containing a bunch of bell peppers. Find the probability of picking a red followed by a green followed by another green, all without replacement. So because this initiates like an ordering, the order of picking out the peppers does matter. What I can do here is the slot method. So red followed by green followed by another green. And it's a little bit different from the slot method questions we have been doing in the past, because the first slot method questions were how many different ways can you do something. This one is a probability, so it's a little bit different. So the probability of picking a red out of the total, well, there happen to be 5 reds out of, what does this all add up to here? Adds up to 15 total peppers to choose from. So 5 of them are red, so 5 out of 15 total. You do not put the red back in the satchel, which means our denominator changed to 14 and then to 13. How many greens are there if you pick the red one out and you don't put it back in? There's 4 green peppers, and then if you pick one of the 4 green peppers out, there's only 3 left to choose from. And so that's what we're multiplying straight across for our slot method. Just remember that this is a probability, therefore we have all of these denominators in the slots. When you crunch this number, this would probably be a calculator question, you end up with 2/91. Okay. Find the probability of randomly picking 3 peppers, choosing a red and 2 greens. So in this case, order doesn't matter. It doesn't say pick a red followed by 2 greens. It's just any combination of red and 2 greens. And so in this case, I'm going to have a fraction again because it's probability. And so if I choose a red and 2 greens, so there are 5 red peppers in the satchel to choose from. I have to pick one of them. So 5, choose 1, and means multiply. Out of the green peppers, there's 4 of them to choose from. I have to choose 2 of them. And then out of the 15 total peppers, I have to choose 3 of them. So this number here should add up to 3. And that's what it does. And so again, that's because it's a probability, so I need the total in the denominator. Okay, so out of 15 peppers, choose 3 of them. These specifics are up here. Out of the 5 reds, pick 1. Out of the 4 greens, pick 2. This gives us, if you type this in your calculator, you can verify this with me, 6/91. Okay, so what's the difference between A and B? Meaning, what's the difference between this and this? Well, first of all, this one is without replacement, and the order matters in this case, the first one. In the second one, the order does not matter. And so what we're going to do is in A, the order mattered. Therefore, we did slot method. And in B, order didn't matter. So we're just doing the combinations. Okay? So fast forward a little bit. Now I want to talk briefly about mutually exclusive. We'll do a very few examples of this, and then we'll continue the discussion in class tomorrow. But a definition of mutually exclusive for you: 2 events that cannot both occur. Another word for this is disjoint. And so actually what this means is, I know you guys have all seen Venn diagrams before. And so you have like event A and event B, and this area in here represents both. And so what if there isn't anybody that falls into this both category? In that case, your circles are disjoint. And that is what mutually exclusive means. It means there is nobody in this overlap. Nobody can be both a Fremd High School student and a Palatine High School student. For example, those 2 circles are disjoint. It's the same thing as being called mutually exclusive. We use both words. So just consider that when you're thinking about mutually exclusive. If those Venn diagram circles do not intersect, that means they are mutually exclusive. Okay? And so a couple more examples besides being enrolled at Fremd and Palatine, which can't happen. You can't have 5th period math and 5th period gym. Those cannot happen simultaneously. So people who have 5th period math would be in circle A. People who have 5th period gym would be in circle B. And there's nobody that falls into both categories because you cannot be scheduled in 2 places at once. Another one, I'm kind of going backwards here. Picking a card that's a black and a diamond. Well, there aren't any cards in the deck that are both black and diamonds because diamonds are red. right? Okay, so here's our two formulas. When we add, the probability of A or B means you add A plus B, but if there are people that fall into both categories, they got double counted, which means you need to subtract the people that fall into the both category away. It's the same thing as adding up every single person here in this A circle, and then also adding up everyone here in this B circle, but that means that you added up these people twice, so that's why you need to subtract it away. But if the events are mutually exclusive, that means that there are 0 people in here. And so in that case, the both category equals 0. And so that's why the formula, the basic formula that we have learned so far for OR is just A plus B. But if they are not mutually exclusive, then you have to subtract away the both category. Let's do just a few examples to introduce this, and then we'll finish it in class, okay? First example, find the probability of choosing a card that is a club or a 3. And so what I'm going to do is probability of club or 3 is probability of club plus probability of 3 minus probability of club and 3. This is the formula. And keep in mind there are some 3s that are clubs. In fact, there's one card that's a 3 and a club. So if you count all the clubs, which there happen to be 13 clubs out of 52, plus all the 3s, there happen to be 4 3s in the deck out of 52, minus, are there any cards that are both clubs and 3s? That have a club and a 3 on them? Well, there happens to be one card that is both a club and a 3. It's called the 3 of clubs. And the reason why I have to subtract it away mathematically is because I counted the 3 of clubs in the club category and in the 3 category. So technically that card was counted twice, which is why I need to subtract it away so that my math is accurate. And the reason why I left everything over 52 instead of reducing all my fractions is so I can easily now combine them. They all are over 52. So I'm going to leave them over 52 and just combine the numerators. So 13 plus 4 is 17, minus 1 is 16. I am able to divide both of those numbers by 4, which gives me 4 over 13. Okay, let's try the next one. Find the probability of choosing a card that is a king or a queen. So probability of king or queen equals probability of king plus probability of queen minus probability king and queen. Okay, so this is just the straight up formula, not thinking at all about whether it's mutually exclusive or not. In this case, there happened to be something in the overlap. So these were not mutually exclusive because that answer wasn't 0. Just this part right here wasn't 0. There is a card that is a club and a 3. There's one card, it's a 3 of clubs. In this case, are there any cards that are both kings and queens? There are no cards that fall into the both categories. So if I'm going to draw the two circles for a Venn diagram, I'm going to have one for kings, one for queens, and there's going to be no overlap because there are no cards in the deck that are both kings and queens. But the probability of being a king, there happen to be 4 kings out of 52. There also happen to be 4 queens out of 52. And there are no cards in the deck that are both kings and queens. So that gives me a grand total of 8 out of 52, which again, you can divide everything there by 4. So you get 2 over 13. And then just to kind of compare and contrast you guys, so this formula that we're using every time when you're subtracting the both people, it works every time, but sometimes the both category is 0. In this case, there was a card that was both a club and a 3. In this case, there are no cards that are both kings and queens. This, the fact that it's 0, means that it is mutually exclusive. Okay, and if you picture the Venn diagram, you have your bubble over here for kings and you have your bubble here for queens, and they do not intersect because none of the cards are both kings and queens. Okay, so keep using that formula. I will pick up with example 3 in class tomorrow, and I'll be able to answer questions and we'll do a lot more practice, okay? That's your introduction to mutually exclusive and dependent events, and I will see you tomorrow. Have a great night.